Hey everyone, I'm going to talk about my final project on the UNINEXT Universal Instance Perception paper and GitHub repo. My project specifically was trying to adapt this code for Google Colab and to get it working on 3 specific subtasks. So the general problem within computer vision is that there's lots of different subtasks associated with computer vision, namely identifying objects based on categories of objects, identifying them and segmenting them within images based on those categories or those names. This goes for both images and for videos. So that's this first category here, category of category names. So the identification of objects based on the category of object. And we can group many different subtasks under that general heading. The second is very interesting. It's called language expressions as the overarching category. And the problem here is trying to direct the perception of a model based on a natural language expression. So there's 3 different subtasks here: referring expression comprehension, referring expression segmentation, and referring video object segmentation. So first 2 for images and the third for video. Then there's target annotations, which is, you could also conceive of as a prompt, but it's a prompt based on annotation. So selecting a particular object by drawing a box around it or segmenting it and asking the machine to track that object over time within a video. This is an example of what we're looking to do with object detection. So identify all the objects and label them with categories. This is an example of what we're looking to do with referring expression comprehension. You can see these are various prompts, and these are the objects identified based on those prompts. So this would be a correct identification of the furthest left plane. Here's an example of target annotations, which is maybe a little the harder one to understand just from verbal description. So in this image, I can identify this little baby penguin, and we would ask the machine to track this baby penguin over each of the images, each of the frames in the video. Same with video instance segmentation. We can color code 3 different objects and visually through a prompt and ask the machine to track them over time. So the idea of UNINEXT, quite interesting, is to unify all of those various computer vision tasks based on a prompt-guided formulation, to see them all as kind of prompts in some way or another, and to unify those tasks based on that prompts. That allows them to create a unified architecture, and also allows them to leverage the vast amount of training data that existed, but which was fragmented across the various tasks. Also, an interesting addition of this network that we'll see on the next slide is the joint embedding of the prompts and the images or the videos using a binary cross-attention mechanism. And as a final output, UNINEXT will identify N object proposals and then look to identify which of those proposals best match the prompts that were initially given. So this is a representation of the architecture. You can see here on the left, we start with prompt generation down here, and there's 3 different modalities of prompt. There are the categories, just the names of all the different objects. And these are essentially hard-coded into the system based on the objects 365 data set and set of categories. So there's 365 categories here, at least. There could be more, I'm not sure. There's also the language expression that the user might give to the system, for example, the giraffe on the right. Or there's also a prompt, which is the target annotation. We could think of the image as a prompt. So these get embedded as the prompt embedding. We also embed the video or the image, input image, via a convolutional net backbone. Now, UNINEXT comes with 3 different out-of-the-box convolutional backbones. I focused on one, which was the ResNet 50 backbone. So we receive an embedding from the convolutional net, and those are combined in this early fusion layer. Then the visual output embedding goes into the transformer encoder and decoder, and the prompt embedding comes back here to meet with the transformer decoder output, where the prompt is used to identify the object proposals over here that best match the input prompts. So whether just a category, the language expression, or the target annotation. I have some detailed notes on each of these steps here. So image and prompt embeddings. As you can see, so the 3 options, again, ResNet 50 as the backbone. There's also ConvNext large and VIT huge. Those are other options that I didn't explore. For prompt embedding, the prompt embedding is a combination, like I said, of these 3 modalities. So expression, category, and target annotation. The early fusion model here is a bidirectional cross-attention module. And this is the way the output embeddings are updated based on the bidirectional cross-attention. Then we have transformer encoder decoder. What's interesting here is they utilize the multi-scale deformable self-attention module. And then finally, we have the instance proposal matching, where the instant prompt matching score S is a product of the the transform of the weight matrix times the target features. So the training data that was used to go into this model, there was actually a lot of different data and a lot of training. As the pre-training, they used the Objects 365 data set, and they used 32 A100 GPUs to conduct the training here. For the image level joint training, this is phase 2. So they did the joint prompt image training on 4 different data sets, primarily COCO image data sets with 16 A100 GPUs. And then finally, phase 3 of fine-tuning was the video level joint embedding training. And again, they used pseudo videos from COCO. So they produced something like videos from the COCO data sets, and then they leveraged additional video segmentation data sets. Again, that was conducted on 16 A100 GPUs. There's a summary of some of those results here. And again, more detail on the data sets. 2 million images in Objects 365 with 30 million bounding boxes. These are all human annotated. COCO training data sets are about 18 gigabytes of images with annotations. And I do provide in the appendix to the Jupyter Notebook a walkthrough of the COCO dataset APIs. Okay, installation, configuration, setup. This is the least fun part of this whole process. Honestly, this was quite difficult, very buggy code base. It seemed like a lot of things had been moved around after they had originally posted it, perhaps. And there were a lot of broken links, a lot of imports weren't working, a lot of paths were hard-coded. I need to backtrack and find all of them and update them for colab. Additionally, there's a lot of missing requirements that were not stated in the installation instructions. So I need to identify those and address those. But once everything was installed, there was actually pretty good results. So for task 1, object identification and detection, these results were quite good. You can see this is an output of one of the tests. And similarly with task 2, referring expression comprehension, this was quite good. In this instance, I gave a prompt of player on left and white, and the model correctly identified this player on the left who was wearing a white shirt. However, task 3, video instance segmentation, this is not good, at least on Colab. It was very difficult to get working. In fact, it didn't work, primarily due to missing codecs within OpenCV at the point where I was attempting to write the video output of the instance segmentation. So if I had more time, or as a next step, I would look into replacing within the source code the OpenCV video writer for another video writer. One thing I wish I had known earlier on in this process, but it's not documented anywhere, is the arguments for executing those outputs that I just showed you. So these are all the configurations that I was able to extract from the source code. You can see it requires a specification of a particular configuration file. There's an option to use webcam as an input for the video. There's also an option to provide a link to the video input. You can also provide multiple inputs separated by a plus sign. I did not test this. You also specify the output path, confidence threshold. This is the confidence threshold over which instance predictions will be shown within the object or within the image. Task, this is an important one. So there's two choices, detection and grounding. Detection is the identification of the objects within the image or the video. Grounding is refers to the expression. So if you use grounding, then you'll want to specify a grounding expression, which can be anything. So this is a free text expression. There's some additional options, but I didn't explore these either. You can see the summary of my test results. So I performed 10 different tests across the 3 categories or the 3 tasks. 70% of them were good. One was okay. One was okay because the model identified correctly the object within the field of vision, which was a wolf, but it mislabeled it because wolf is not in its vocabulary. So bear was, and it thought the wolf was a bear. So not bad. One not good on the referring expression comprehension. This was due to a prompt where I asked it to select more than one object. However, by the nature of the model itself, it can only output one proposal for an object identified by natural language expression. So that's just an inherent limitation. So maybe it's fine, but I was just testing it to see what would happen. In summary, I do recommend continuing to explore this. It was the code is, like I said, quite buggy, at least for Colab, but I'm starting to get it to work. And I think with a few more weeks, I could get the rest of it to work, and I could explore some of the other computer vision subtasks, which I didn't have time to do. Could also explore other convolutional net backbones and see if I can find areas where the larger convolutional nets actually perform better. However, like I said, it is very difficult to debug and to run this code. There's still the issue with the codecs that affects all of the video. And you may, just as again, as a warning, you may run into a hard-coded path, which will cause you problems. So if you're doing this in Google Colab, I recommend you just replicate my folder path exactly so you don't run into as many of these problems. Thank you.